My name is Nadim. Thank you all very much for coming again to our second Real World Crypto Meetup. Yay. Hooray, yay. Success. Whoopee. Yeah, the point of this event, which is co-organized by Hylé and Symbolic Software in collaboration with our sponsors, is to give Paris some breathing room to talk about cool stuff and for people to meet up. It's inherent to people in the field to be kind of like socially awkward and introverted, but make an effort. Talk to each other, you know. So that's what we're here for. And listening to cool talks. So just a few points before we start. First, you may have noticed that we decided to charge 10 euros for entry this time. Why did we do this? We're not making money off of this event. I just want this to be perfectly clear. The reason why we added this charge is to be able to make this a sustainable event. So we can use those funds to get a nicer space, get you guys snacks, which we're going to have at the end of the event. And so even with that, small fee, and even with the very generous contributions of our sponsors, which I'll get to in a bit, this event still costs money, but we're okay with this. Like but we want this to be sustainable. So thank you very much for agreeing to pay this small fee. This is not like a for-profit thing. Excuse me. Yeah. Just wanted to make that perfectly clear because I don't want there to be any misunderstandings. Like we're not aiming to make this ever a for-profit thing. So, okay. Before we begin, we're gonna just say a quick thank you to our sponsors, and a couple of our sponsors are gonna give a 5-minute presentation about them, and then we'll get started with the talk. So, a quick thank you to our sponsors. Starkware, wow, they do proofs and they have a blockchain. You can deploy your apps. They built Cairo. That's a really smart thing, and it's named after a city. We also have the Open Source Technology Improvement Fund, which secures open source for the world. Wow, look at that. It looks like a bee made it. Incredible. There's a lot of companies there. Okay, those numbers, boy, are they big. And now we have Zama. You can build applications with fully homomorphic encryption. There's a rotating cube and more cubes in a isometric perspective. Okay, wow, look at that. Sure looks like a manifesto to me. Isn't that exciting? Okay, moving on to Hylé. Think outside the block. Get it? Blockchain? Think outside the blockchain? Yay, they sure love the color orange. Even in outer space, things are orange. Thanks to Hylé. And last but not least, Symbolic Software, which I have a presentation for, so I'll give that. Thank you. Quick presentation about Symbolic Software, my company, which is sponsoring this event. So what do? Over the past 7 years, we've conducted over 250 security audits, from pacemakers to password managers. We've audited critical software tool chains for, Ethereum Foundation, Mozilla, Linux Foundation, and many other companies. We do audits. So cool auditing thing based in Paris. Our audits are neat. This is one of our reports. Look, it has words and figures. So you'll get that if you do an audit with us. We know how to make sentences. We also publish research software for cryptographers. Namely, it's more targeting students and engineers. So there's VerifPal, which is a tool for learning how to analyze protocols, and Noise Explorer, which also provides formally verified implementations of cryptographic protocols. So check them out. Our research approach is more geared towards education, as you can see from the fact that I ship research software with a manga in it, which does not earn me a lot of respect amongst academics, especially in France. And we also make puzzle games. So there's, Dr. Kabushi's Labyrinthine Laboratory, a really nice puzzle game for Nintendo Switch, PC, Mac, and Linux. And look, you can check out the trailer. It's really nice. Let's take a look. Yes, that's a thing that we made. Thank you. Also, did you know that in Japan, there's a variant of chess called shogi? Well, now you do. And you can download an app that lets you play it on your iPhone and Android device. In fact, a variant of it called mini shogi, because the board is smaller. And so you can play this. It's called Runes of Ardun. We made it, and it's free. So yeah, that's a good thing. So if you need a great audit delivered on time, or you want to try out accessible cryptography research software, or play a fun puzzle game, because that's a great way to diversify a cybersecurity business, you can check out Symbolic Software. And don't forget to enjoy today's event. And now up for our next sponsor, Hylé. Come on up, Sylve.
What's up, folks? I'll be probably less fun than Nadim because I don't know how I can top that. So what do we do at Hylé? That's the tagline, ZK is a bullet train without a track. There's a very weird thing that happened in history where blockchain is a thing that happened before the productization of ZK, where we had like actual usable ZK stack like ZK VMs, Noir, and Cairo. So we're now reverse engineering everything to cram ZK back into blockchains, and we do these humongous things called ZK EVMs, which are a terrible mistake. So that actually really constrains you, because if you want to use ZK for building an application and you want to go on the blockchain, you're stuck. So what do? You use Hylé. We're a blockchain that's specifically tailored for what we call provable applications. So whichever language you use, Noir, Cairo, ZK VM, even Rust, if you don't really want to care about using any circuit, that's what we do. Hylé is a network that sequences your transactions, settles them, because we're running native verifiers as part of consensus. You do not have to write a Solidity contract, deploy it on the EVM, and have it run somewhere. You just get that out of the box, and that's it. So we are happy to be sponsoring this event, and in particular, Matteo, who's somewhere over there. We have a grant program if you want to build with ZK actual applications and not try to optimize the BLS curve on the plonky double binius something. If you actually want to ship things into production, I see you laugh and I know you know why. If you actually want to build applications and ship them to prod, come and talk with us. That's actually what we want to build. That's all for me.
So we also have the sponsor from Zama, who's going to give a quick spiel about Zama.
So I will explain the cool blocks here. Hello everybody, I'm Jason, ecosystem lead at Zama. So Zama is a cryptography company. We are building a new toy for you guys. So there are many toys, zero knowledge proofs, hash functions. We are building FHE, fully homomorphic encryption. It means that you can do computation over encrypted data. And everything we do is fully open source. So we have core libraries for two industries, AI and blockchain. I mostly focus on blockchain. And on blockchain, basically, what we provide is an FHE VM, so an EVM with FHE capabilities, which means that you can send encrypted states in your smart contract and run encrypted states. A very simple example of this is you can launch, for example, a private ERC20, the same as USDC or USDT or any token where the state is private, so only you can decrypt it, or the sender or the receiver, or any logic on top of it. And so for the first time, we at least have cool confidentiality on the blockchain. There are other ways to do confidentiality in blockchain, like ZK, but we believe that FHE is better because we have composability with all the smart contracts. You don't need to compute any proof. Everything happens on chain. You can put identity data on chain for the first time, and many other cool stuff. So thank you, everybody.
So let's get started. The first talk is from Dfns. We're going to be talking about hashing structured data. How hard can that be? Take it away, Denis.
Hi, I'm Denis. I'm lead MBC engineer at Dfns. I'm very excited to be here. As I said, it's way out of my comfort zone. My laptop is falling. Okay, so before I start, I just give you a bit of context about our company. We are doing threshold signing schemes. We developed two protocols. We developed a whole ecosystem for threshold schemes. So if you want to use them, here you go. So hash functions. We are going to talk about hash functions. Why am I describing what hash function is it in a room full of cryptographers? You will see. So hash function, it's a function that takes a byte string, one byte string as an input, and outputs output of hash function that is hash. Hash function is required to be collision resistant, meaning that we can't find two different byte strings that give the same hash. Okay, so when we build a threshold TCD-SA, threshold signing scheme is a complex cryptography protocol, but it's composed of simple blocks like hash functions, Pierre encryption, elliptic curve cryptography, something else, and when you know all the building blocks, you can build a complex threshold scheme, which we observed that people do. They know basic blocks, they build threshold schemes. So when you want to build a threshold scheme, you just search it, you can find it, and then you just build it. That's a simple stuff because you just do stuff that you got used to. You just sample primes, you generate some data, and then something catches your eye. We see that the hash function takes several arguments, and we have no idea what it means, because as you remember, hash function only takes one argument as an input. And here you struggle to understand what the author meant, because nowhere in the paper it is mentioned what hash function means. Nowhere it's mentioned what it means to call with multiple arguments, and hash functions are not even mentioned in preliminaries. And do remember that most of the cryptography is developed in startups where you're pressed by deadlines, so when you have to ship as fast as you can for your company to survive. So what most of developers do when they see this, they just concatenate it, because it's sort of logical thing to do, because well, you might think that this different arguments is just you chain everything. Well, there is some logic, and many companies, many implementations have done this, as you will see. What we did is called ambiguous encoding, and it breaks security of entire protocol. It allows attacker to recover the full private key from one malicious participant. Why it is bad? Because when we concatenate two strings, we lose information where the strings were concatenated, and that lets attacker to find two different set of inputs that result into the same encoding and that give collision. And hash functions are supposed to be collision resistant, and that's the whole purpose of the hash functions. So how does actually can be exploited? You can see in this paper, I didn't have time to explain this. So a alpha shuffle attack described in TSS shock. There is a QR code. That's very smart attack. It's very fun to read. And many libraries were affected by this attack. So many libraries actually did what I described on a previous slide. They concatenated the inputs. What we need for our protocol to be secure is unambiguous encoding. Unambiguous encoding is a function that takes any structured data and it outputs an encoding of this hash function, of this data. And it needs to be one-to-one function for this to be secure, which means that for each data, each structured data, there only one encoding. Which also can be explained that there should be a decode function. We don't need to implement decode function, but it's a good intuition for you to have. When we can't decode encoding back to original value, it's ambiguous encoding, and we should fix this. Second, the unambiguous encoding has to be reproducible. Which has some engineering challenges. For example, if you're working with usize, esize, if you don't know Rust, it's a machine size word. It's different on each platform, and you need to be very careful when you serialize it. And the same with the hash map. If you're not familiar with Rust, it's a hash it's structure that stores values in randomized order. So you can't traverse this structure in deterministic order across all your instances. You need to think about you need to make your encoding function reproducible. So when we have encoding, all we do is just hash encoding of the structured data, and that's what we call unambiguous encoding. So whenever we see this in the paper, what we actually have to do is this. We need to encode the data and hash it. How do we implement unambiguous encoding? The trick is very easy, very simple. We just need to encode the length of the byte string that we encode into the encoding, and then it's already unambiguous enough. And that can be implemented in the Rust. And although the idea was pretty simple, the implementation is not as smooth as we wanted. We have their unwraps. They can cause panic in the production code, and it's a taboo in the production code. We don't do this. But here, why we have to do this? Because length of the byte string is machine word, and we can't encode it. So we have to convert it to some integer with fixed size. But no computer can allocate more than 2 to the power of 64 bytes, hopefully. So it should work like for 1,000 years without breaking system. So returning back to the paper that we've been discussing. If we translate all the inputs to the Rust structure, it's this. And it's more difficult than what we expected it to be. So it contains a lot of data, and it's a bit of problem because the code of encoding will be very elaborate. But also we have a list of byte strings that we need to encode. Why is it a problem? Because we don't know how to encode lists, and this is another trick that we have to do to encode a list. We encode a length of the list into the encoding, but it's not perfect. To make it even more unambiguous, we need to put a tag into the encodings. So we basically need to disambiguate the encoding by putting tags. Okay. Now back to original challenge. This is how it's supposed to be written in the paper. Why authors thought it's not worth mentioning that they require unambiguous encoding, I don't know, because this is not trivial to know that this actually should correspond to this. In the code, well, that's a lot of code. Just enjoy it. That's 58 lines of code that we need to write, and imagine writing it. Imagine reviewing, auditing, maintaining it. Imagine that there is somewhere a typo, and you have to find it because, well, you get hell bored when you write this. And of course, no sane person will write it, except me for presentation. But I wrote it. I hope you appreciate the effort. Well, actually, you won't write it because here you will see when you look closer that there is some repeating patterns, and you can do some engineering magic to make it like to reuse some codes to reduce amount of repeating patterns. And in the end of the process, you will discover that you have built a library for unambiguous encoding. That's what we did. We built a library. You can use it in Rust. It provides very easy interface for digesting, for hashing structured data. It just accepts hash data and outputs a hash. So if you implement something in Rust, here you go. And well, for example, before we just, this is what you need to write for our data to be digestible. And there is so many reasons for you to use this. It's the best unambiguous encoding library in Rust because it's the only library in Rust for unambiguous encoding. Also, it's no STD, no alloc, WASM friendly, and it has a lot of features. Thanks.
Hi everyone. I'm Cyprien. I'm with 3MI Labs, so we're like a sort of new research lab in Leuven. We're very close to where COSIC is, which is part of the university. And today I'm gonna give you a little introduction to a new signature scheme that one day could be, we were talking with Al from Polygon, and they were like, okay, so everybody uses ECDSA because that's what you should use because it's secure and it's standardized and everything. But in our system, it means we have to handle it. And the systems we've built aren't really designed to handle ECDSA. So it would be good if we had like a purpose-made signature scheme that was still kind of cryptographically secure and done in the right way and stuff. But that would work a lot more with our proving system when we were verifying it. And so we were like, well, why don't you just use your proving system and make a signature scheme out of it? How bad can it be? So the next 10 minutes are going to be about details and numbers on the resulting signature scheme, which you can read the paper here. I don't know if the slides will be available, but for the link for later. Cool. So how do you build a signature scheme from a zero knowledge proof of knowledge? The first thing you have to do is choose a hard problem, a one-way function, and then your secret key is going to be the input, and then so that's your signing key, and the public key is going to be the output. So that when you give your public key, because it's one way and it's hard, nobody can find your secret key. You give a proof that you know the secret key, that it gives the right public key. You use a commitment scheme. You make the whole proof non-interactive, and that's where you kind of shove your message into it. And then you get a signature out the other end. So that's kind of the design pattern that's existed for a long time because Schnorr, for example, I can't use ECDSA because ECDSA doesn't actually work quite like this, but Schnorr does. So your hard problem is just discrete logarithm. So your public key is big X, your signing key is little x. You put that into the Schnorr identification scheme. And in this case, your commitment is also just discrete logarithm. So when you commit to the randomness little a, what you do is you send big A to the verifier. But for this, you don't need a hash function. But then you kind of Fiat Shamir this by hashing, and we've learned how to do hashing properly now, so you can do that. That's where you shove your message into the hash function, and at the end of the day, you get your Schnorr sort of signature as it's supposed to be. So we're going to follow this design, except we don't want this because doing this kind of maths inside proof system is not nice at all. And we don't want Schnorr. We want something that's kind of compatible with what the Stark proving system that Polygon already had. So let's get into it. The first thing we talk about is the rescue prime optimized hash function, also known as RPO. So you've got your finite field, which is very nice because it's like exactly 64 bytes and it's got nice properties to compute, wrap around and stuff like this. You take your 12 element state and you shove it through a bunch of very mathematical operations. So matrix multiplication, just vector addition, exponentiation by some value alpha, and then you repeat more multiplication, addition by another round constant, and then another exponentiation by 1 to the alpha. So you notice there's no like SBox, there's no bit shifting, byte shifting, all of this kind of stuff that CPUs are really good at doing, but actually proving systems are really bad at handling. So Rescue Prime Optimized was really designed to be arithmetic as much as possible. So you put your message in the top 8, and you have these like bottom 4 that are just carried over. You do 7 times this whole thing, or 7 times this whole thing, and then you get your hash at the other side. Okay, so that's the hash function we're going to work with for the hard problem. That's what we're going to replace discrete logarithm with. Then you need something to prove your hash function computation. So this is where you get an interactive oracle proof for algebraic intermediate representation. What this AIR means is literally just you have a computation. So you've got your successive states in the row, and your columns are like your registers, like your CPU register. So you can make columns out of this, and then you can define constraints, which are like polynomial equations. And if your execution trace satisfies the constraints, if it's a valid trace for the computation you want to prove, then these polynomials will nullify, which means that they divide and blah, blah, blah. There's mathematics in there. But essentially what you want is you want an execution trace and you want constraints. So when you have RPO, we take the execution trace, you start with the initial state, which is just going to be your secret key, 4 elements filled in, and just zeros on either side of it. You're going to go through the 7 applications of this matrix, add, and stuff until you get to the bottom state. And that's going to contain your public key in the first 4 elements in the middle. So that's what your execution trace is going to look like. Then you got to express the constraints. What are the constraints that make it a valid execution trace? The first constraint is the first 4 and the last 4 should be 0. So you write some polynomials that mean this. The last constraint is the middle 4 things should be your public key. So you write some polynomials that mean this. And in the middle you say, well, each row should be the round function output of the previous row. So then again, you write some polynomials that mean this. They're like degree 7, so it's not too bad. It's not great, but it's not too bad. So you've got RPO, you've got an execution trace for it, you've got constraints for it. So now you have a signature scheme. Your hard problem is RPO of your secret key. We used the Deep Alley plus Fry kind of interactive Oracle proof system. We use like a Merkle tree commitment scheme with a hash function. We use the BCS transform, which is like an iterative version of the Fiat-Shamir transform. So Fiat-Shamir, you've only got one thing in and then a thing out and then you're done. But IOPs, you've got many more rounds. So there's something called the BCS transform and you should do it right. There's many ways of messing up hashing in these things. But you still kind of put your message into it and get your signature out. And the reason why this is kind of nice, it's because the Deep Alley IOP has an efficient AIR for its own verification circuit. So that means that if I make a signature using this scheme, someone can prove that they verified my signature quite efficiently, much more efficiently than they can prove that they verified, well, maybe not ECDSA, but ECDSA is not post-quantum secure. So they can definitely prove it more efficiently than they verified some kind of lattice-based or complicated, non-algebraic friendly post-quantum signature scheme. So that's kind of where the design motivation came from. So I've talked about the Deets. I can give you some numbers because I talked about a lot of things. There's like finite field arithmetic, polynomials, proof systems, things like this. So these are the numbers. So you can choose to implement the hash function either with Blake 3, which is very good for your CPU, or RPO, which is less good for your CPU, but good to be used in a proof system later on. You can multi-thread it if you want. So some of you might have noticed there's no units, right? What's numbers without units? How many of you think these timings are in seconds? And Nadim can't answer because I sent him the slides. No? No one thinks seconds? Really? Come on. How many of you think milliseconds? Okay. How many of you think minutes? No? Okay, microseconds? Oh, okay. I like your optimism, guys. No, it's milliseconds. It's milliseconds and kilobytes for the signature size. So, yeah, 10 millisecond signing when you're hashing with Blake 3. Like, I think given kind of the complexity of the thing, that's a pretty decent result, given that we kind of just threw in a bunch of components together. Now, the little thing is like, this is in what we call the list decoding regime. But if you go to the unique decoding regime, you have to change your parameters a little bit, and then signing time goes up. And this is the setting you would want if your signature is going to be verified by a proof system further on. And you have to use RPO so that this proof system is efficient. But you can see that still you can sign in about 400 milliseconds. Like, I know that doesn't compete with ECDSA. It doesn't even compete with some of the best candidates in the last NIST competition. But a user is not really going to notice 400 milliseconds. And we can probably optimize some more stuff out of that. Okay, so these are kind of standalone numbers. And the last slide I have is about Sorry, I copy-pasted that from the paper. I couldn't redo it. We're down there. I know the people at the back can't really see that. But if you look at, so we have Ziggy and Prion, which are both kind of built on exactly the same model as us. And Ziggy takes more than 100 milliseconds to sign, and Prion is in seconds. There's Faced, which takes like almost less than a millisecond to sign, but that is heavily based on symmetric key cryptography and not proving system friendly at all. And I'm allowed to say that because I kind of co-wrote the spec for it. But then you've got some of the more, so like Picnic 3, Sphinx, and Dilithium. These are from the kind of the OG NIST competition for other post-quantum candidates. And you see like they're in the tens to hundreds of milliseconds. So really we don't compare that badly. But I have to say, most of these are implemented using, for example, Shake as the hash function, as opposed to Blake 3, because Blake 3 is not a NIST standard, so you can't submit candidates to the NIST if you're not using all of the NIST standardized things. Faced has to use AES as the hard problem. They can't just use RPO, because NIST is going to be like, what's RPO? Yeah. That's me. Those are my co-authors, Shahla and Al. Thanks to them for their help, and I'll take any further questions if there are any.
Working at Ledger, so I'm Vincent. I'm managing the product security at Ledger, which is famous for the dungeons, a team focused on the product security. And Pierre, if you want to introduce yourself.
Yeah, Pierre, I'm a principal engineer at Ledger, and I'm working on innovation stuff and a lot of other topics.
Super. So what I like, and by the way, when we see a room with almost full room on cryptography stuff, something is changing. And thank you for the organization. So basically, I'm sure that you are all familiar with blockchain, and we think there are 3 properties that you can find on any blockchains: authentication, integrity, and obviously on non-repudiations. But the thing is that when you try to provide a UX, a good user experience on blockchain, a big piece is missing: confidentiality. Typically, just if you want to try to attach some metadata to your wallet, let's say your name, it's very complicated today on if you want to support every blockchain. And some commodities that you got every day, if you take a photo with your iPhone, easily we can find the same photo on the on the iCloud, on your laptop. The thing is that Apple knows you, and Apple tracks you. And at Ledger, we don't want to store any user data. Okay, so we don't want to know you. It's true that we have some analytics to know you, to know your usage, but we can't track you. Okay, and today we are suffering from that, from user experience. I don't know if some of you are user of Ledgers, but basically if you create a wallet on your mobile, you need to create the same wallet on your desktop. That's a nightmare. And that's why we have decided to start from the beginning. We think that hardware devices are very good to store secrets. And today there are many focus on authentications and signature scheme. Okay, so typically managing your digital assets. But the reality is we think that it's also a good starting point to share some data in a full privacy way. Okay, and I will let the floor to Pierre, but we thought the protocol to be open. Okay, today we will be very focused on Ledger, but I will be very happy to discuss with you many use cases.
Thank you. Hi, everyone. So I will present a bit how it works. It will remain very high level, so if you have questions, don't hesitate to go ask us. So basically, the main principle of the protocol, it's keying. The goal is to be able to share encryption keys with someone else. Why we designed this? Basically, it was to implement something called selective disclosure. So there is one simple way to do this. You have a full document with a lot of items in it. And if you want to share part of the document, the easy way to do it is just encrypting each items in the document with an encryption key, and you just share the key to someone. And that's basically the idea behind the keying. So we have the ability to duplicate a key and give it to someone, an application, a service. You can also revoke a key because at some point you may not trust the application, the service anymore. And we also have some features to enable what is called here master key that allow you to open group of safes. So basically it means that with one key I'm able to open multiple safes and I can kind of group my data. And the whole goal of this is to be able to manage this from a hardware device, a hardware wallet, with restricting resources. So the protocol is organized around two main data structures. We have what we call a stream and a tree. So basically, a stream is protecting a single encryption key. The goal is to have the state of all the members who have access to this encryption key, and also to store a key. Basically, on the hardware device, we don't have a lot of storage space. So the idea is that we need to externalize this encryption keys, have a backup somewhere, resolve our context at some point to be able to share the key again. And we want to manage everything from the hardware device. On the streams are organized like basically a blockchain. So you have blocks of data. Each block is signed by an issuer private key. And inside this block you have commands. So we have multiple types of commands, but basically it's to initialize the stream, share it with someone, add someone to the stream, share a public key, this kind of things. Every single block is chained together with a reference from the parent block hash. And we have a second data structure, which is the tree. And the tree basically represents every encryption keys you can have in the keyring. And at the end, it looks like something like this. And the tree is actually deterministic. So to generate new secrets, we don't use the secrets inside the hardware wallet, because obviously we want to share the secrets with someone else. So we don't want to share internal secrets. We just share secrets generated for these use cases. And so yeah, the root is basically the seed of your keyring. And from this seed, we are just using BIP32 to be able to derive new private keys, new extended private keys. So I was talking about encryption key from the beginning, but it's actually extended private keys everywhere. Just at some point, when you need to do encryption, you just need to transform your private key into a symmetric encryption key or use a different scheme. And so why did we use a tree to manage all of this? And it's basically a challenge we have with hardware wallets. It's the value of hardware wallet is basically its secure display. The goal is to be able to send some data to the hardware wallet. It needs to do some checking. You need to check if the operation seems legit. But at some point, the ownership of the asset, the decision remains in the hand of the user. So our goal is to be able to, from technical data, to display something meaningful for the user. And that's one part where the tree is very useful, because basically with the tree, you have derivation path. So it's basically the position of a command stream, a stream inside the tree. And with a strict policy, basically we are able to do two things with this derivation path. You have an example here of derivation path with 0h, 16h, etc. And depending on how you construct this path, basically we will be able to say to get a stable ID from this derivation path. And from a stable ID, it's very easy to just map it with a mapping table. You can map it to something human readable, like the gift wish list here. And it's also interesting for the second part, which is revoking access to a key. So obviously, you cannot just say to the application, hey, just forget about the key. You need to generate a new one. And we can basically do it by just having some components in this derivation path to be just about versioning the key, basically. So here in this example, we have M0H, so that's version 0 of the key. And if I want to create a new one, I just derive at M1H. I have a new key, and I have a new subtree, so I can recreate everything, basically. The interesting part is that the hardware wallet can be a bit lazy, meaning that if you want to share the full document, you don't have to share every single key. We can just share the parent key, and automatically the software will have access to everything. Yeah, I will skip this one because Vincent already talked about it. Yeah, and in terms of cryptography, it's very common. The goal was mainly portability with existing systems. So all encryption inside the blocks. So basically we are encrypting encryption key. And we are doing this with AES, GCM. Every time we have an encryption, we will compute an encryption key with ECDHE. The goal is for this, so we encrypt it once, and only the reader can decrypt it later. Only the recipient of the key will be able to decrypt it. And finally, we are using the same curve as Bitcoin and sign-in block with ECDSA. So yeah, in the protocol we can adapt a bit. We can change the algorithm depending on the version of the protocol. And yeah, so basically this this protocol can be used in multiple kind of application. So we already have some ideas how to use it. And yeah, actually one interesting fact about the characteristic of the tree and of this whole architecture is that basically it works a bit like a certification chain. So basically for this feature, synchronizing Ledger Live applications, one interesting part is that you will basically certify the application you are using. And at this point, we can do some soft authentication with our backend, with other services. You just add, for example, your mobile application to the keyring. And at this point, we are able to authentify, making sure that you are using authentified application. So you can do some certification stuff with it. And yeah, I think that's it for me. Thank you.
So today I will present what I've been working on the last month, the Provable email game engine. So first, who am I? I'm Matteo. I like ZK. I like to build cool ZK apps in general. And I like chess as well. You'll see why quickly. So the first thing the start of the project was play-by-mail games. Play-by-mail games have been there since mail exists, basically, with like Go and chess most of the time. But actually, there has been, I think, in the 80s, like a lot of play-by-mail game that have been created. Like if you go on the Wikipedia page, there's like much more than I thought. And the idea was to basically make them provable with using emails. You'll see. So here, I made a library to make any play-by-mail game provable, but I made an example with correspondence chess, which also where it's the most obvious case. And so yeah, make it provable as well. So I've been using multiple tools for that. The first one is, of course, ZK email, which is a library that allows to verify that a certain email has been sent. Because emails are signed, the idea is that it's a circuit that verifies the signatures, and then you can extract whatever information you need from the body. So here, in my example with chess, I will like extract the move and extract the chessboard that has been sent in the mail. So yeah. That's the idea. And then I use RISC-0 because it's much easier than building a chess engine myself. I just use a library called Shakmati in Rust, and I can just verify the moves by myself with Shakmati instead of writing the whole thing. And RISC-0 is a ZK VM, so you just can verify any Rust code. It creates stars. So that's the idea. And everything will be proven on Hylé, which is the sponsor of the event, and also the sponsor of this project. And it allows to, it's a, yeah, you had the intro earlier, but it's a lean blockchain for a provable application. And the idea with Hylé is that you can settle the proofs easily and then maybe verify them on Ethereum later. Like you have your two proofs, you verify them on Hylé, and then maybe you add a bet that you made on Ethereum, and you can claim, okay, I won this bet, instead of verifying the Stark on Ethereum directly. So yeah. So this is a more in-depth architecture slide, but I've made like the library in Rust that listen for new emails, and when there is a new email, it calls a function that you have to implement yourself, because as I said, it's for any chess by mail game. And on this case, it's check if the mail is a valid move, if the move is a checkmate, and store the moves into the DB. And if the move is a checkmate, it actually proves the mail, because I actually only, this is an interesting part of the design, I only need the last two moves to be proven for the entire game to be valid, because since every mail is signed, if you sign a mail, you basically say, okay, I think this board is the board I'm playing on, and if you get checkmated on the next move, then you cannot deny that you did it. And then I go back on the referee lib and prove with zk email and re0, like what I was explaining earlier, extracting the move and verifying that the move is checkmate in a zk proof. So I do it once just to check every move, but I only prove one checkmate move and the move before, actually. And then, yeah, Hylé enforces that the inputs are the same. Sorry, maybe it's a bit small, but I will I will share the slide, and also it's in the repo. Ensure that the two proofs are using the same inputs, because you don't have like one move that is checkmate and one move that your opponent played. And it verifies the proof. And also, yeah. Oh yeah, demo time. So we're gonna say the move we want to play as the first move. So here E4, which is like a standard notation for chess, and saying new game against myself. So here the message is sent, and we need to wait a bit for the mail to arrive on the other. Okay, wait a second. Oh, I didn't send it. I need to do it again because I didn't make the server online before the presentation. So, referee and CC new game 2. And it should be good now. So we're gonna wait for the server to catch the mail and verify it, as I explained just before. Should be pretty fast, I think, but depending on the internet connection, we can check. Oh yeah, the server caught it, and now we have a new valid move with the board, but because it's zoomed. Okay, so now what's gonna happen is we're having here a representation of the chessboard, and we have to pass it to every in every mail we're doing. As it's called a fen. I think the name is because of the name of the authors. It's the standard notation for a chessboard in chess. And we're playing f6, which is a very bad move, but it's the fastest mate possible in chess, because I don't want the demo to be very long. So we're gonna wait a bit. Actually, we have to wait. This mail is not the right one. Okay. Okay, I played f6 now. So I'm gonna answer. Okay. No, I won't play, I don't know, bishop c4, I think is a valid move. Bishop to c4, okay. And passing the actual board here. And yeah, this is the thing with the demo. It's like I cannot do much. I just have to wait for the mails to to arrive. Still not the right one. Should be pretty soon now. Okay. Now we're gonna play the move that will make a checkmate for our opponent, g5, which is not a good move to play. I don't particularly advise this opening to you guys. It's okay, we're gonna wait for the server again. Okay. So he's taking his time.
So which is slower? Is it email or is it ZK?
Right now it's email. Maybe it's Gmail, yeah? I mean, it's implementation based. So like, as I said in the architecture, like you have a process mail function. So if you want to have timestamp and stuff, you could implement it yourself. Like, it's just like the referee lib is like not taking any side on what are the rules that you want to implement. So yeah, you could do it. So I got the move here. And now we're gonna play checkmate. So move queen to h5 mate. Oh, no. Queen. And again, passing the board. Also the UX I've chosen is not the best right now, but we could also make it better very easily. And now if we look at the server, it's gonna realize it's a mate and create the risk zero proof and broadcast it to Hylé. As you can see, it's not my fault. The server is fetching a lot. Okay, so now the proof is, you can see the risk zero proof has been successfully proven, I think, and we need to wait for some reason. And then we're gonna broadcast it on Hylé. This has been broadcast, and now if we go back to our mail server, we have, oh, we won by checkmate. And yeah, so there, now it's verified and the proof has been generated. So yeah. If we quickly go back, I have a joke from Sylv, which is this one, me during the demo. So yeah, oh yeah, the future of this project is you guys can contribute easily, create new games, improve my game if you want. We could also implement Hylé very easily because Hylé is a blockchain, it has a state, so we could just, when something happens on Hylé, could say, okay, oh, I create a risk zero proof that my Hylé is like 10 more. So okay, now the proof on Hylé is working well, and yeah, you could do betting with on Ethereum and then give the proof to get the bet or something like this sort of stuff. So yeah.